Hello and welcome to the second video of the FP2 chapter second order differential equations. On the screen, a quick starter to review the previous video, complete this table. You need to remember that if an auxiliary equation has two real roots, then the complementary function has the form y equals a e to the alpha x plus b e to the beta x. If there's only one repeated root, then it should be a plus bx times e to the alpha x, and if the roots are a complex conjugate pair, then you need y is equal to e to the px times a cosine qx plus b sine qx. These are the general forms of the solution for a second order homogeneous equation where it equals 0. We're going to use this and we will solve second order non-homogeneous differential equations that look like this. We use it because the auxiliary equation tells us the complementary function, and the solution to a non-homogeneous differential equation still uses the complementary function. It's just not the only part of the solution. We need a second part of the solution, which is called the particular integral. So for equations of this form, with some function of x on the right hand side, the general solution is the complementary function, which we did in the previous video, solving the homogeneous version of this, plus a particular integral. That's what we're going to focus on in this video. So the complementary function comes from this as before. The particular integral is dependent upon what this function is, heavily dependent. It will often have the same general form. That's because as you have this part here, the complementary function, when you put this into this expression, you get 0. So that disappears as you put that in. But what we want here is not 0, we want some function of x. So as you differentiate and put this in here, we need something extra that will follow this expression to give us this answer. And although we know it should be the same general form, that doesn't tell us exactly what it is. We need a little bit of work to find that out. So if f of x is a constant, then try a constant. If f of x is a linear expression, try a general linear expression like this. You can see where I'm going with this. If it's quadratic, try a general quadratic expression. If it's e to the wx, where w is a known constant, so if it's e to the 3x, for example, then try some constant times e to the 3x. So match the exponential with what you've been given and put an unknown constant in front, which we'll talk about how to find in a moment. And all of these will work because as you differentiate them, you don't get anything you can't handle. Here, if you differentiate this, it just disappears to 0. Here, when you differentiate this, you get a constant from this term, and that can interact with the constant in the original function. Same here, as you differentiate this, the mu can interact with the nu, the lambda can interact with the mu. When you differentiate it again, the lambda can interact with the constants as well. Here, we've talked about this before, when you differentiate this, it can interact with itself. So when we come to these three, we need to be careful. When you differentiate sine, you get a cosine. So to allow for interaction there, to get the right constants, you need to allow for both a sine and a cosine. Again, match whatever this is. If this is a minus 2x, then use minus 2x as the argument, but lambda and mu will be unknowns initially, and you'll have to find out what they are. Same with the cosine, use a mix, and obviously if it is a mix, then still use a mix. And sometimes you'll find one or more of these constants are 0. For example, with a quadratic, you might just find that lambda is the only number that's non-zero. Okay, that's fine. But you need to allow for the possibility that these are non-zero as well. So we start with these general forms, and then you need to find what lambda and mu are, and you do that just by substituting this into your differential equation. You can focus on the particular integral without worrying about the complementary function, because you know when you substitute that in, that will always equal 0. That's the whole point of the complementary function. So you can just use these expressions and then put your final particular integral expression together with your complementary function at the very end. You don't need to memorize all of these as such. You just need to remember that whatever f of x is, use some generalized version of the same thing. So we'll do 3 examples of this, then a final note and a final example at the very end. Find the general solution of this differential equation. So the first thing you need to do is check, is it homogeneous or non-homogeneous? If it's homogeneous, you need to do the complementary function. If it's non-homogeneous like this, you need to do the complementary function and the particular integral. So we still need to do that complementary function. Now I'm going to use y to mean slightly different things as I go through this. So to be very clear, I'll put CF. Any y that comes under this heading is the complementary function only. To do this, we need the auxiliary equation like we had before. We've got a second derivative with no coefficient, so that's a 1, so that's m squared. And the first derivative has a coefficient 5, and the function y has a coefficient of 6. So this is our auxiliary equation. Solve this as per normal. Here we have 2 real roots, 3 and 2. So our complementary function is y equals a e to the 3x plus b e to the 2x. And that's the complementary function. This is not the final y. Now we need the particular integral. So I'll use y again, but now y is specifically for the particular integral. Here, on the right-hand side, I've got a linear expression. So the particular integral that I'm going to try, and I'll write try here because this doesn't always work. We'll talk about that for the final example. I'm going to try y equals lambda x plus mu. Now it's important to realize that lambda and mu are different to a and b. Obviously they're different numbers, but what I mean is a and b are constants of integration which you will find only if you have boundary conditions and need to find the particular solution. We need the general solution, so we won't ever know what a and b are in this solution. That is not the case with lambda and mu. These are not constants of integration. These are unknown numbers that I need to find in order to know what this particular integral is. And that's why we do what we're about to do, which is to differentiate this once, twice, put it all in to find out what lambda and mu are going to be. So the first derivative here is lambda, and the second derivative is a 0. So when we put that into this equation here, we get a 0 minus 5 times the first derivative, which is lambda, plus 6 times the original function, the particular integral, lambda x plus mu. So that's 6 lambda x plus 6 mu, and that has to equal 2x. And you don't need to worry about the complementary function, because when you put this in, as I said earlier, the whole point of that is that it will equal 0 on the front. And that will always be the case. Now to find out what lambda and mu are, we need to equate the coefficients. We can see here that we've got 6 lambda x and 2x. So 6 lambda must equal 2 in order for this to work. And then our constants minus 5 lambda plus 6 mu have to equal 0 constants on the right hand side. So that's minus 5 lambda plus 6 mu equals 0, and then you solve your simultaneous equations. Fairly easy here, lambda is 1/3, so here 6 mu is equal to 5/3, which makes mu equal to 5/18. So my particular integral is equal to 1/3 x plus 5/18. Now I've used y in 2 different ways in 2 different parts, that's why I had these mini subheadings here. The last y is my general solution, so I would always write this as CF plus PI first to make it clear that now you're adding these two together to get your final general solution, and that is AE to the 3x plus BE to the 2x plus 1/3 x plus 5/18, and this is the final general solution of this non-homogeneous equation. From this point, to find a and b, the constants of integration, you would need boundary conditions, and that would be the particular solution. Now, because we're focused on the particular integral in this video, the next 2 examples will have the same equation on the left-hand side, so it will be the same complementary function each time, and I'm just going to change the function on the right. So here, our complementary function is still going to be AE to the 3x plus BE to the 2x because the same coefficients are here. But the particular integral here is a quadratic. So for our particular integral, I'm going to try y is equal to a general quadratic, lambda x squared plus mu x plus nu. And if we do that, the first derivative is 2 lambda x plus mu, and the second derivative is equal to 2 lambda. Now to find out what these three constants are, I need to put it into this equation here. So the second derivative is just one of those, so that's 2 lambda. First derivative, there's minus 5 of these, so that's minus 10 lambda x minus 5 mu. And the function, the particular integral that I'm trying, is 6 of these, so we've got 6 lambda x squared plus 6 mu x plus 6 nu. I'm running out of space, but all of that has to equal 3x squared. Now we equate our coefficients. We've got 6 lambda x squared must equal 3x squared, so 6 lambda must equal 3. That's a nice one. And then our x's, we've got 0 x's on the right hand side. We've got minus 10 lambda x plus 6 mu x, so that has to equal 0. And we've got a 0 constant on the right hand side as well, so 2 lambda minus 5 mu plus 6 nu must equal 0. Now we go ahead and work them out. Lambda must equal a half, so here we've got minus 5 plus 6 mu equals 0, so mu must equal 5/6. And then here we've got 1 minus 25/6 plus 6 nu equals 0, so that's 25 minus 6 is 19/6 is 6 nu, so nu is equal to 19/36. That means our particular integral, y is equal to 1/2 of x squared plus 5/6 x plus 19/36. So that gives a final general solution, complementary function plus particular integral of ae to the 3x plus be to the 2x plus a half x squared plus 5/6 x plus 19/36. Third example, again the same coefficients on the left hand side, different function on the right, so our complementary function for this is still ae to the 3x plus be to the 2x. Our particular integral, I'm going to try y is equal to lambda times cosine 3x, because that 3x matches this 3x, and a mu sine 3x. So the first derivative is minus 3 lambda sine 3x plus 3 mu cosine 3x, and the second derivative minus 9 lambda cosine 3x minus 9 mu sine 3x. Then we have to put this into here and make it equal to 13 sine 3x. That gives us minus 9 lambda cosine 3x minus 9 mu sine 3x. And then just be careful, we've got minus 5 lots of this, so that's plus 15 lambda sine 3x minus 15 mu cosine 3x, and 6 lots of the original particular integral, so that's 6 lambda cos 3x plus 6 mu sine 3x, and all of that has to equal 13 sine 3x, and obviously 0 cosine 3x. Splitting those two off to make our simultaneous equations gives us minus 9 lambda minus 15 mu plus 6 lambda for cosine, so that has to equal 0. For sine, we get minus 9 mu plus 15 lambda plus 6 mu equals 13. Solving these, we have minus 3 lambda equals 15 mu here, so lambda is equal to minus 5 mu. Over here we've got minus 3 mu plus 15 lambda equals 13, and now we know lambda is equal to minus 5 mu. That gives us minus 3 mu minus 75 mu equals 13, minus 78 mu equals 13, and that divides nicely to give mu equals minus 1/6. Substituting that back in gives us lambda equals 5/6, and now we can get our particular integral, which must be 5/6 cosine 3x minus 1/6 sine 3x. Final step, as per the others, complementary function plus the particular integral gives us a final general solution of a e to the 3x plus b e to the 2x plus 5/6 cosine 3x minus 1/6 sine 3x. So once you've got the general idea of how to do the complementary function, and you know the three different forms that you could get, and you know the general idea of how to do the particular integral, you know how to match what the function is here to the particular integral that you're going to try and use, it's more or less the same thing every time. You don't get quite the same variation as you do with first order differential equations, which could end up as pretty much anything, depending on the question. However, there is one final note, and that is that sometimes what you try to use for the particular integral and what you have with the complementary function, the terms might be able to interact. And if that's the case, you'll find something funny goes on. So occasionally a particular integral might contain the same type of term as the complementary function. A simple example is if the particular integral involves e to the something x, which you know is going to come up in your complementary function somewhere. What you will end up with is when you substitute your equations for the particular integral into the second order differential equation, you won't get a solution. If I go back for a second, here, when we tried to get the solution here, we ended up with two simultaneous equations. We could solve them and get answers. What I mean is you'll end up with something silly like 7 equals 9, and you simply won't have a solution. If that happens, don't panic. Just multiply your particular integral by x. If it's e to the something x, try x e to the something x instead. If that doesn't work, very occasionally that won't work, just multiply by x squared instead. And at the sort of level we're working at A level, one of those should work. So a quick example of this: new equation, new complementary function needed, particular integral needed as well. So we've got the complementary function. Auxiliary equation is m squared plus m equals 0. So we've got m plus 1, which does give us two real solutions, but one of them is 0. So y is equal to a e to the 0x just gives us a, plus b e to the minus x. Then we try our particular integral, and normally I would look at this and say, okay, it's a linear expression. Let's try a linear expression for the particular integral. And I'll follow this through to show that it doesn't work, because if we differentiate this, we get lambda, and if we do the second derivative, of course we get 0. So when I put those in to the equation here to find out what is lambda and mu, we end up with 0 plus lambda equals 2x plus 3. When we try to equate these, we end up with lambda equals 3. That seems fine, but then we end up with 0 x's on the left and 2 x's on the right, and if you tried to equate that, you would end up with the expression 0 equals 2, which of course is simply not true. So here there's no solution. There's simply no way of choosing a number for lambda and mu that will allow this to be true. And that's why, although I actually didn't do it this time, I usually write a little try on there, because you're trying it. There's no guarantee it will work. That didn't work. So instead, try something new, multiplying by x. So I'm going to try lambda x squared plus mu x. But instead of leaving it at that, I will put a nu in. I don't need to, but I'm going to because it gives me an opportunity to say something later about nu. So the derivative of this is equal to 2 lambda x plus mu, and the second derivative is equal to 2 lambda. Now if I put this in, I get 2 lambda plus 2 lambda x plus mu has to equal 2x plus 3. And this I can solve. 2 lambda is my x coefficient, so that has to equal 2. And then 2 lambda plus mu has to equal 3 for the constant. That means lambda is equal to 1, so mu must also equal 1. Now the thing about nu here, I didn't get a nu from this, and I just wanted to note that that's a different situation to something like this. Not having any information about nu, that's very different to a statement that simply isn't true, or is impossible to solve. But I don't want to let nu equal anything, I want to let it equal 0. I'm happy to let all of the constants just fall into the a. So we've got our particular integral of x squared plus x. The general solution then is the complementary function plus the particular integral, which is a plus b e to the minus x plus x squared plus x. I hope that is enough for you now to have a go at the questions in exercise 6b, and maybe I'll see you in the next video for particular solutions.